I mean, we're tackling some big problems out there, from climate change to curing diseases.
It really makes you wonder, are we doing everything we can to speed things up?
Exactly. And that's what's got me so fascinated by this whole area of physics-informed machine learning.
It's definitely a mouthful.
It is. But trust me, the potential is huge. We're talking about using AI to not just analyze data, but to actually understand and solve complex equations from physics.
And engineering.
Oh, yeah. And even medicine. And we've got just the thing to help us unpack it all, a new paper called From Pins to Pecans, Recent Advances in Physics-Informed Machine Learning.
It's like a crash course in the future of scientific discovery.
So let's dive in. First things first, PINs. What are they and why are people making such a fuss about them?
Right, so PNNs stand for physics-informed neural networks.
Okay, so neural networks we kind of get, but where does the physics-informed part come in?
Well, think about it this way. Imagine you're an engineer trying to design something really complex, like a supersonic jet. You've got all these equations from physics that describe how air flows over the wings.
Right, like lift and drag and all that.
Exactly. But solving those equations for a shape that intricate, it's a computational nightmare. Traditionally, we've used methods like the finite element method, FEM. Basically, you break the complex shape into a bunch of tiny, simpler shapes.
Like building with Legos, right?
Yeah, exactly. It works, but it can be incredibly time-consuming and computationally expensive, especially as the problem gets more and more complex.
So PNNs offer a way around that.
In a way, yeah. Instead of trying to force the problem to fit our existing methods, PNNs actually incorporate the laws of physics directly into the neural network itself.
So instead of just crunching numbers,
Yeah.
these PNNs are learning the underlying physics. Wow. So how did that work in practice?
That's where things get really interesting. It all comes down to something called automatic differentiation.
Ah, derivatives. I haven't heard that word since, well, calculus class, I guess.
Right. But basically, automatic differentiation lets these PNNs handle all those complex calculations that we normally associate with physics and engineering derivatives, integrals, you name it, without us having to program them in explicitly.
So it's not just about making the math easier. It's about giving these AIs the ability to solve problems that would have been impossible or just impractically slow before.
Exactly. And that's where we start to see the real-world impact. We're talking about designing better aircraft, developing more effective drugs, understanding complex systems like never before.
This is already blowing my mind, and we're just getting started. Okay, so PINNs are already blowing my mind, but this paper doesn't stop there. It goes on to introduce something called PCAN's Physics-Informed Kolmogorov-Arnold Networks.
Yeah, they really threw the whole alphabet soup at us with this one.
Right. PCANs. Break that one down for me.
Okay, so remember how we were saying PNs typically use multi-layer perceptrons, MLPs, as their kind of base? Well, PCANs, they use a different kind of network structure. And the inspiration actually goes all the way back to the work of a mathematician named Andrei Kolmogorov back in the 1950s.
Wow, the 50s. That seems like a lifetime ago in AI years.
Right, but that's the cool thing, seeing these connections across different fields and eras. Anyway, Kolmogorov, he did some really important work showing that any continuous function, the kind we're often dealing with in physics and engineering, can actually be represented as a combination of simpler functions.
Interesting.
So PCANs take advantage of that by using a network structure that can better capture those underlying relationships.
So it's like we're giving these AIs a more efficient way to represent and process complex information, kind of like upgrading the engine in our AI race car.
I like that analogy. Same basic concept as PNs, but with some significant performance enhancements. Let's go back to that supersonic jet example for a sec. If you were trying to model the airflow over that really complex wing structure using traditional methods,
I'm with you.
you'd need this super dense mesh of points to even begin to approximate the shape, which would lead to some really crazy computational costs. But PCANs, because they leverage Kolmogorov's theory, they can actually achieve similar accuracy with a much simpler representation.
So we're talking about potentially designing and testing things in like a fraction of the time.
Exactly. And it's not just about speed either. It's about being able to tackle problems that would have been completely intractable before. And the applications, they go way beyond just aircraft design. We're seeing PNs and PCANs being used in fields like biomedicine.
Oh, wow. Like how?
One really promising area is personalized cancer treatment. So imagine being able to use a PNN to model tumor growth based on a patient's unique medical data.
That would be incredible. Truly personalized medicine.
Exactly. And then you could potentially use that model to optimize radiation therapy to target the tumor more effectively while minimizing damage to healthy tissue.
That's remarkable. And to think
Yeah.
this is just one application. What else are we seeing out there?
Okay.
Honestly, the list goes on and on. In fluid and solid mechanics, we're seeing PINNs used to design more efficient aircraft engines, understand the complex flow of blood in our arteries, even predict earthquakes with greater accuracy.
Hold on, predict earthquakes. Are we talking about early warning systems here?
That's the ultimate goal. Of course, the Earth's crust is incredibly complex, and the data we have is inherently messy and incomplete, but researchers are making progress.
So using these pin ends and pecans, we could potentially save countless lives.
Exactly. And it's not just about natural disasters either. We're talking about everything from optimizing the design of power grids to developing new materials with incredible properties. It's like we've given these AIs a crash course in the fundamental laws of the universe and then unleashed them on our biggest challenges.
And we're just scratching the surface here. It's mind-blowing to think we can now equip AI with the very laws of physics, but with all this potential.
Hmm.
I do have to wonder, what are the challenges? I mean, this technology is still relatively new, right?
Oh, it is. And like any scientific revolution, there are hurdles to overcome. And I'd say one of the big ones is figuring out how to best train these PNs and pecans.
Because they're so complex.
It's more like we've got these race cars with incredible power, but we're still fine-tuning the engine to get that peak performance.
I see. So what needs fine-tuning?
Well, researchers are constantly exploring new network architectures, so basically experimenting with different ways to structure the AI's internal workings.
To make them more efficient.
Exactly. It's not just about making them faster, it's about making them smarter about how they use their processing power.
Makes sense? And then there's the data itself.
Oh, yeah, that's another huge challenge, dealing with the inherent uncertainty in real-world data.
Which is basically unavoidable.
Pretty much, yeah. Think about those earthquake predictions we were talking about. I mean, the Earth's crust is unbelievably complex, and the data we collect is inherently messy and incomplete.
So how do you even begin to teach an AI to make accurate predictions when the information it's working with is imperfect?
That, in a nutshell, is the million-dollar question. Researchers are developing all sorts of sophisticated techniques to help pins and pecans account for this uncertainty, essentially teaching them to make educated guesses based on incomplete information.
So it's almost like we're not just teaching these AIs physics, we're teaching them how to deal with the ambiguity of the real world.
Exactly. It's a whole other level of intelligence, and all of this is to say that while the potential of this technology is absolutely enormous, it's still a work in progress, which honestly is part of what makes it so exciting. There's so much more to discover, so many breakthroughs waiting to happen.
It really does feel like we're standing at the edge of a whole new frontier in science and engineering.
Absolutely. And the ability to combine our knowledge of the physical world with the power of AI, it's opening doors we never even thought possible. Who knows what incredible discoveries await us in the years to come?
One thing's for sure. The next time I hear the acronyms PNNs or pecans, I won't just be reaching for a scientific dictionary.
You'll know it's the sound of science accelerating, pushing the boundaries of what's possible, and potentially changing the world as we know it.
Well said. And on that note, thanks for joining us for this deep dive.